Good morning. Welcome back. I wrote here the main things that I want you to keep in mind today and for the rest of your life, at least your professional life. Q would always represent for us a belief system, which is another way of saying a model. Your model, somebody else's model. What you think is the real state of the world. The real state of the world is defined by not by knowing what's going to happen, but by knowing the probability of any possible outcome. And we're always talking here about outcomes that are mutually exclusive and jointly comprehensive. In all of these events that we're talking about that could happen, coin being head or tail, we're assuming that it's definitely going to land either on head or on tail, never on both and never on neither. So mutually exclusive events and jointly comprehensive, they cover the whole picture. Q is one particular subjective belief or model. I will sometimes use parentheses to remind you it's a function of the event. So it takes a particular possible outcome as an argument. And sometimes I'll just put a bar on top of it to remind you that it's an array, a vector, as opposed to a particular one probability. Okay, it's a probability array or probability distribution. You don't need to do that. I'll just move this out of the way. Is this better? A little more. Okay. P is the same thing, except P is the truth. The true distribution, the true state of the world, over the same set of events. And you may know it, or you may not know it, depending on the setting. In the real world, we usually don't know it. And we will deal today with this very important distinction between when you know it, when you don't know it, and what do you do when you don't know it. This is our fundamental unit of information, and it is subjective because it depends on your subjective belief. And now the next two entities are really important, and the difference between them, the subtle difference between them, is really, really important. This one is simply taking, the way I wrote it here is a summation over events that come from the distribution P. Okay, this is this twiddle symbol, means it comes from this distribution. And then we're measuring the surprise of these events according to some distribution Q. And we divide by n, so we're taking the average. This is the average surprise of model Q on events drawn from distribution P. If I drew 100 events from distribution P today, measure the surprise of distribution Q, which is assumed to be fixed, and average that, I get some number. Tomorrow, I come in and I draw another 100 events from distribution P. Same distribution P as yesterday, or as the day before. And I again measure my average surprise there. Will I get the same number? Wake up, you guys. All right, anybody who thinks we will get the same number, could you please raise your hand? All right, that means everybody's with the program. All right, why will you not get the same number?
Because it's a distribution and you just draw randomly from a distribution.
Because it's based on a random draw, a random sample. If I draw 100 events from distribution P today and 100 events from distribution P tomorrow, it's not the same 100 events. So this quantity is a random quantity, or it's a random variable. Some people use the word random to mean arbitrary. Not a good idea. I don't mean arbitrary here. And some people use the word random to mean uniformly drawn. That's not a good use either. When I say random here, I mean that it is not a fixed number. It has different values on different attempts. and maybe it has a distribution of values. So if I try to estimate the height of people in the US by drawing 100 uniformly random people, drawing 100 people and measuring the height and averaging that, that may be a reasonable estimate, but if I do the same thing again, I will not get the exact same number because I did not get the exact same people. And if I do it again and again and again and again, every time I get a slightly different answer, and you can imagine there's a distribution to that number, to that average. Some values are more likely than others. This is called the sample distribution of the samples that are drawn. So this is a random variable in the sense that it can take on different values at different times depending on the sample. Contrast that with this entity, the cross entropy. This entity is not a random quantity. It is a fixed, calculable entity as long as you know P and Q and you can carry out the calculation. It is defined as the expectation of the surprise of Q on a single event drawn from P. This would be summation of the surprise of Q on E, weighted by how likely this E is, how likely it is according to the true distribution P. And this summation is over all possible event types, all possible types of events. There's no n involved here. This is not a finite sample. This is a complete enumeration of all possible events. So in the case of talking about a coin with a head and tail, this is a summation over only two values, two summands. Whereas this could be, n could be 100 or 1,000 or any other large number. Or this could be a summation over 10 events, or it could be a summation over 1,000,000 events. But the idea is that these are different event types, not actual occurrences, but event types. This is why we call this summation by type. And this is called summation do you remember the term? By token. As long as P and Q remain the same, this calculation would always give the same number. You can think of this as the true value of something, of the expected surprise, and this as a sample approximation of it. The next entity we discussed is self-entropy, the special case of cross-entropy, where the cross-entropy is from P to P itself. This is a very fundamental unit. I called it self-entropy, but often it's just called entropy. It is the most fundamental unit of information theory, I would say, maybe after the concept of information. It was one of the greatest contributions of Chanin to information theory, or to the world. I'd like to write it in a variety of ways. It is, of course, the cross-entropy of P and P. I can write it like this: the expected value of the surprise of P under the distribution P. So that's another way of writing something like this. This is the expected value of the surprise of Q under the distribution P. So when I write a subscript for E, that means expectation under this distribution. If it's not clear what is distributed according to this, I might even write E according to P, E twiddle P. E is the random variable that comes from this distribution. So one way of writing it is E of P, I of P. Another way of writing it is explicitly sum of P to the P of E times log of 1 over P of E, summation by type over all types E. And yet the third way of writing it is taking the negative out and writing simply some pi log pi. This time I'm using the index I to mean the same thing as I mean here, event type. I'm deliberately changing the notation so that you see it in other places, it's not confusing. You will often see something like this, negative pi log pi. Those of you who take physics, if you've taken the statistical mechanics or thermodynamics, you may very well have come across this entity, something that looks like this, in physics. In fact, the concept of entropy has existed in physics for much longer than it did in information theory. Ludwig Boltzmann was a physicist in, I think, 1800s, who is considered the father of thermodynamics and statistical mechanics. And he has made heavy use of the concept of physical entropy. Physical entropy is a very fundamental concept in physics. It has some physical interpretation. It has a mathematical form very similar to this. The meanings are somewhat different, but they're also very, very similar. To distinguish between them, we call them physical entropy or informational entropy. The formula is kind of the same, and you can definitely make arguments for the connection. The story goes that when Claude Shannon was inventing information theory, and he showed his what he was doing to von Neumann, who was maybe the greatest computer scientist of the time, except it wasn't called computer science then, it was called cybernetics. Von Neumann suggested to him that he call it entropy. He called this quantity that he came up with entropy because he said nobody really understands what entropy is, so nobody could really criticize you. Which was kind of true, because entropy is a hard concept in physics to understand. Entropy has many interpretations, and I'd like to go over some of them, and many uses. First of all, remember that it's a function of a single distribution. Okay, so entropy, you can think of as it's a single number measured, say, in bits. It's a function from a distribution into a number. And further, we know that the number is positive, or at least non-negative. And for a finite set of events, we know it's also bounded by a log of the number of events. All that we know already. Entropy can be thought of as measuring the degree of uniformity of the distribution over the different events. So if you have k possible outcomes, the most uniform distribution is the uniform distribution. It has the highest possible entropy. There's log k bits. In the other extreme is the most skewed distribution, is the one that puts all of the weight on one event and no probability, zero probability, all the others. This is entropy 0. But you could use entropy as a measure. It's not the only measure, but it's a very reasonable measure of where a certain distribution is in between the completely focused, completely concentrated, and the completely flat. So one interpretation is it's a measure of skewness. I'll put skewness in quotes because there's a technical term, skew, that measures a particular form of skewness, and I don't want you to confuse it with that, or uniformity. Of course, skewness is the opposite of uniformity. But there are other much more important interpretations or ways of understanding entropy. One important interpretation comes from coding theory, which is the original reason, one of the original reasons Claude Shannon developed the theory. Coding theory deals with how to assign different codes to different outcomes so that you can communicate, transmit these outcomes long distances with minimum error or with correcting those errors and with minimum effort. So think of the problem as, let's say you're running an experiment, you're running it again and again and again, and you need to communicate the sequence of outcomes that happened for the first experiment, second experiment, and so forth, to somebody who's across a very expensive telephone line. Now, you guys don't know what expensive telephone lines are with WhatsApp and all of that. You grew up in a world where communication is pretty much free, but in the 40s, communication was anything but free. It was expensive, and the longer the distance, the more expensive it was. And not only was it expensive, so you're trying to communicate this information in as few bits as possible, but it was also noisy. Different channels of communication had different amounts of noise in them. And the problem that Claude Shannon dealt with was how to design codes that would be, on one hand, as efficient as possible, use as few bits as possible on average, and at the same time might alert the other side in the case that some of the information was garbled. And in a more fancier version, not only alert them, but also tell them what was garbled so they can correct it. So we call these things error detecting and error correction. And error correcting codes are a very interesting and still open field of inquiry in math and information theory, how to design most efficient codes. Imagine you have a set of possible outcomes. So these are event types, E1, E2, E3, EK. Design a code for this means assigning a bit string, not necessarily a fixed length bit string, to these events. So if you imagine that k is 16, you can simply assign 0, 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, 1. That's a code, a very simple code, not necessarily the most efficient code. If you want a more efficient code, you might ask yourself which of these events is most common and assign it a short code. And then which is the next most common and assign it also a short code, if you still have room in your short codes. And keep doing that such that the more common events get shorter codes and the less common events get longer code, because common events will happen by definition more often you will transmit short codes. So if you look at the average length of a message consisting of many, many codes, you will end up using fewer than 4 bits on average. This is a result of the fundamental observation that there are fewer short codes than there are long codes. Codes of 2 bits, there are only 4 of them. Codes of 10 bits, there are 1,024. So this very simplistic way of designing this code that I just described, that sort the events by their probability, assuming you know their probability, and then assign codes starting from the shortest to the longest, is known as Huffman coding. Huffman coding is, in general, more efficient than the simplistic way of assigning codes that I gave here, but it's not necessarily the most efficient. And people have spent a lot of time designing more and more efficient codes. As you might imagine, to design an efficient code, you need to understand not only P, the true distribution of the event probabilities, but you might also suspect that events depend on one another. So you might look at conditional probabilities and codes that take into account what happened earlier. Back to entropy. One of the fundamental things that Shannon showed, actually 2 things, 2 fundamental theorems. One is, once you know P, and you calculate the entropy of the source from P using this formula, sum of pi log pi, that number is an absolute lower bound on how efficient you can make any code. In other words, there do not exist codes that use on average fewer than this many bits per event. Okay, so Chanin Theorem number 1. I don't remember if it's considered this first theorem or second and then third, so I'll just call it theorem number 1. Given a distribution this is P1, Pk. There does not exist no code there are no codes are more efficient than h of p bits per event. If you measure the efficiency of codes as the average number of bits per event over a long sequence of events, by calculating the entropy, you got yourself a guaranteed, mathematically guaranteed lower bound on how efficient they can get. Which is extremely useful because if you design a code, and these can be hard to design, good ones, and you want to know if you want to spend another year trying to find a better code, this tells you whether you've reached the limit or you're far away from it. The second thing that Chanin showed, very related, is that not only is this a lower bound, it is a tight lower bound, meaning that for any distribution P, there exist codes whose efficiency comes arbitrarily close to the entropy limit. It would have been nice to say that for any distribution P, there exists at least one code whose efficiency is exactly the entropy. But it's not quite right. It's almost right. You can get arbitrarily close to this limit. You can get arbitrarily close to this entropy. And he didn't just prove that it exists. He actually showed constructively how you construct such codes. Now, they could become very hairy, very complicated, and maybe not very useful because of that. But in principle, they exist. So there are codes. There exist codes that are arbitrarily whose efficiency is arbitrarily close to the entropy P. What do you mean by arbitrarily close? If you want it to be closer than 0.001, I can find you one that's closer than 0.001. If you want it to be closer than 0.000001, I can find you a code that's closer than that. It's the same meaning as in calculus class that hopefully you all took. So this is just a bit of information theory, but the important take-home message is that entropy can be thought of as the capacity, or the limit, rather, on the capacity of limit on information rate. How many bits you need to describe events. You can think of coding, here's the next step, you can think of coding as a way of compressing information about events. I mean, if I didn't care about efficiency, I could just yell to the other person, oh, the first experiment had this outcome, and the second experiment had this outcome. I don't have to be careful about how efficient I am. But if I want to be efficient, because the communication is expensive, I'm going to compress that information about what the outcome was for each event into the smallest possible number of bits. So this also came out of Chanin. Coding is the same as compression. Not exactly. Coding is a lot more than compression because you might choose to optimize not only compressibility, but also error correction, error detection and error correction, in which case you're balancing compression ability with other properties that you want the code to have. Maybe error resistance or whatever have you. But in the simplistic part of this, if you only care about, if you're not worried about errors, you only care about efficiency, you can think of coding as a form of compression, and therefore the entropy as a bound on how much you can compress things. And if you manage to get a code whose efficiency is the same, meets exactly the entropy of the source, what comes out is uncompressible, incompressible, incompressible, what's the word? Not compressible. Do any of you use compression of any form? So way back when the world was black and white, disk space was expensive. And we didn't have big disks. They had kilobytes and maybe a megabyte, and they were always getting full. You don't know about that world, do you? In the previous century, in the previous millennium. So efficiency of storage was important, and we would often compress our files. Do you compress your files? Do you use .z or? Yeah, okay, on occasion. Why bother? I don't know. But yeah, I mean, there's still, long distance sending of large files is still a bit of a problem. Maybe not for long. Under these conditions, you want good compression. And good compression means as efficient, compress as much as possible, but also don't spend too much time computing the compression and the decompression, right? If you take a regular text file and you try to compress it, how much does it compress? Yeah?
Depends on what's inside the text file.
It depends very much on what's inside the text file. If the text file is very repetitive, it'll compress a lot. If it's not so repetitive, less. But there's a rough phenomena that you typically compress it by about a factor of 3. So if you have a 100 megabyte corpus of text, it'll go down to 30-some megabytes. The compression algorithm that's most commonly used for text is called Lempel-Ziv compression. It's named after two people who came up with it. Or LZ. Several variations on the same algorithm, but it's very commonly used by zip, all the zip packages. It's an adaptive form of compression, meaning that it's not a fixed code, but it's a code that constantly modifies itself as it sees more and more examples because it estimates P better. It still falls into the rules of Chanin, namely, it is a form of compression and it is bounded by the entropy of the text. So you can say if there is a code that is guaranteed to transmit every character or every piece of text with a third of the amount of space we take when we normally type it, that means the true entropy of text is no more than a third of, is no less than a third. Sorry. Is no more than a third. So every time you find a code, you design a code that has a certain level of efficiency, you know that the entropy must be less than that, less or equal. What is the true entropy of natural language? You can express that as bits per character or bits per word. What is the true entropy of natural language, like English or Chinese or Hindi or any other language? Nobody knows? You're correct. Nobody knows. Nobody knows. So this is a very important point. We don't know the true entropy of natural sources, natural events, because we don't know the true distributions. So if you're about to model something in the natural world, like radioactive radiation from the sun, or natural language, or images on the web, or anything that you find, we typically don't know the distribution of things we find. So we don't know its entropy. So we don't know if we design a code for it, or if we try to compress it, we don't know what the limit is. So the important point about entropy is that it's a bound, tight bound, on coding efficiency and equivalently on compression. If we know it, we know what the bound is. If we don't know it, we don't. Questions so far? What am I missing here? Okay. All right. Once we have these down pat, I want to switch to talking about the entropy and the uncertainty in different variables as they relate to one another. So far we talked about a single random variable. The random variable was the outcome of the experiment. I call that random variable big E, and it takes on values from E1, E2, E3 through EK. Now I'm going to switch my terminology a little bit. I'm going to call the random variables X and Y. I'm going to do it, A, to just give you practice and seeing that you can use other letters, but B, because I have in mind eventually learning from X about Y. If you remember from our motivation for information theory, we're thinking of machine learning not necessarily as finding the deterministic function from X to Y, but as using X to reduce the uncertainty in Y. So now I'll talk about two random variables, X and Y. They take on values little x and little y. So the story I tell for that is that you live in a high-rise, in an apartment, and every morning you have to decide what to wear. You would like to know whether it's a hot day or a cold day, and you would also like to know if it's a humid day or a not so humid day. And so there are two variables you're interested in and you don't know much about. The temperature, which for simplicity is either hot, mild, or cold. All right, you will need to figure that out on your own because the assignment is due on Monday. If you can't, we will postpone it to Wednesday. Okay? Try to read online both my slides and watch my lecture from previous year. Learn about mutual information, okay? We're talking about the interaction of two different random variables. Later we'll talk about more. We call them X and Y. At this point, there won't be much difference between them, but we're aiming towards a situation where we're trying to learn from X about Y. The story I'm telling you is that you live somewhere and you wonder when you wake up in the morning whether it's a hot day or a mild day or a cold day. You collect data over a large period of time. Over many, many days, and you use that to estimate the true distribution of the temperature. And let's assume here, for simplicity, that you estimated it very well. So you know the truth. We are here in a situation where we know P. We know the truth. It is 30%, 50%, and 20% respectively. And if you have this distribution over possible values of every day, could be either cold, hot, or mild, you can calculate the entropy of that information, and you just plug it into the formula, and you get a certain number of bits, 1.48548 bits, and that's not surprising. This is roughly what you expect when you have three outcomes. If the three outcomes were equally likely, the number would be slightly higher, right? Higher. At the same time, you also collect another piece of information, which is the humidity, and that's a binary random variable. Takes on only two values, high or low, And again, you observed 60% of the time it's low, and we assume that that's a perfect estimation, and therefore you have a known P distribution here, and you can calculate its entropy, and you get to slightly less than 1 bit. And again, that shouldn't be surprising because we're slightly off from the uniform 50-50. If we were at 50-50, it would be exactly 1 bit. Any deviation would be less than 1 bit. Okay? So far, so good. Important to note that temperature and humidity are not independent, meaning that the probability of a particular combination of values of temperature, particular small t and the particular small m, is not necessarily, that probability is not necessarily equal to the product of the probability of t times the probability of m. These are called marginals, and this is the joint. And the joint is not equal to the product of the marginals. But since you collected that data jointly, every day you recorded both temperature and humidity, you can actually collect the complete joint probability table. And as soon as they let me, I'm going to switch. And here is the joint probability distribution of these two random variables. It's a 2x3 table. It has 6 values. These 6 values form a distribution, so they must sum to 1 if you sum over these 6 entries. And I added, for convenience, also the marginals. Now you know why we call them marginals, because they're in the margin, either the bottom margin or the right margin. And either way of summation gives you 1. Okay? This should be familiar. I copied for you, again, the entropy of the temperature distribution and the entropy of the humidity distribution. And just for the fun of it, I added them together, just to see what I get. So remember, entropy can be thought of as uncertainty, the uncertainty of the temperature plus the uncertainty of the humidity. Now, I will define a joint entropy as follows. I will look at the 6 possible types of days that there are: hot, high humidity, hot, low humidity, mild, high humidity, and so forth. And I will view that as a single random variable that takes on 6 different values. This is a commonly used way of thinking, so make sure you get that. You can take any 2 random variables, put them together, squint, and pretend that it's a single random variable that takes on as values all possible combinations. So here we have a 2-way random variable, a 3-way random variable, and I tend to view it together as if it were a single 6-way random variable. And when I do that, I have a joint distribution, those 6 values, and I can define the joint entropy. The joint entropy is simply the entropy of these 6 values taken from the table. You can think of the joint entropy as the joint uncertainty in knowing the temperature and the humidity. And now I make a fundamental observation that the joint entropy, 2.32, is strictly less than the sum of the individual entropies. This will always be the case, no matter what the joint distribution is. It would always be less or equal, and it will only be equal when, a little louder mumble, when they're independent. That's very true. If and only if the 2 random variables are independent, then the joint entropy would be the sum of the entropies. In any other case, any kind of dependence, doesn't matter what kind of dependence, any kind of dependence means that the joint entropy would be less than the sum of the entropies. This makes a lot of sense if you think of entropies as uncertainty. When 2 random variables are dependent, that means they tell you something about each other. They're related. And therefore, knowing one means that you know something about the other. You reduced your uncertainty about the other. So if you want to know how much uncertainty you have overall, figure out how much uncertainty you have in one, but then what's left is not the original uncertainty of the other, but whatever it is that about the other that you still don't know after you were told about the first one. So variables tell you things about each other unless they're independent. I'm going to now define a few other concepts that are related to these. First, conditional entropy. So I take my joint distribution table and I divide it by the bottom margin to get a conditional distribution table. So this is the probability of temperature condition on a particular value of humidity. This time, every row is a distribution. I define the conditional entropy of temperature conditioned on the humidity being low as the entropy of the distribution of temperature under the conditions that humidity is low, which I read from the top row. 1, 6, 4, 6, and 1, 6. These, of course, must sum to 1. And this is that entropy, 1.25 bits. And similarly, I define the entropy of temperature under the condition that humidity is high. And I get a different number here. And now I define the average conditional entropy. And I write it as H of T slash M. And in some books, you will find that slash forward. And sometimes you'll find it as a standard conditioning. The important thing is that we're conditioning not on an event, but we're conditioning on a random variable. Okay? So it's fundamentally different than this. This is conditioning on an event. This is conditioning on a random variable. What does that mean? Conditioning on a random variable is a weighted combination of conditioning on events weighted by how likely this event is. That's why it's called the average, or weighted average conditional entropy. Also has other names. So I just plug in here the value I calculated here, and I plug in here the value I calculated here, and these 6.6 and 0.4 come from the previous table where we saw the temperature had that distribution. And it's a weighted combination of these two numbers, and not surprisingly, it's in between them. And now we can go back to the question of quantifying the question of how much does humidity tell us on average about the temperature. And to answer that question, we say this is how much uncertainty was in the temperature before I knew anything. This is the entropy of temperature. And this is how much uncertainty remains in the temperature on average if I'm told the humidity. What does this quantity mean? It means that on some days I'm told that humidity is high, and the amount of uncertainty then is this. The remaining uncertainty in temperature is this. On other days, I'm told that humidity is low, so the remaining uncertainty is actually this. So on different days, depending on what the value of humidity is, I'm left with a different amount of uncertainty. What I'm asking here is how much uncertainty I'm left with on average. I'm weighting the two. The reason that's important to me is I want to know how much to pay for the information about humidity. Suppose I can buy a humidity meter and stick it outside the window, and I want to quantify how much is that worth to me. Well, on humid days it might be worth more than on non-humid days, but I'm buying it once, so I want to know how much it's worth on average. Okay? So this is how much it's worth on average. It's how much is left on average, subtracted from how much uncertainty I had before. And when I do this subtraction, I get 0.1345 bits. Okay. I can do the opposite. I can consider buying, instead of buying a humidity meter, I can consider buying a thermometer. Either or. And stick the thermometer out and use that information to reduce my uncertainty about humidity. Okay? So I'm going to repeat this exercise, but I'm going to start with a different conditional probability table. Instead of temperature condition humidity, it's going to be humidity condition and temperature. I go back to the joint distribution, and now I divide by the right-hand marginals. I repeat the exact same derivation, this time conditioning the entropy of humidity on all three possible values of temperature. I have three different answers depending on what temperature is. And I again calculate the conditional entropy of humidity, the average conditional entropy of humidity, condition on temperature. Same formula, different numbers, and I get a different number here. Now I can use that to answer how much does temperature tell me about humidity. Before I asked how much humidity told me about temperature. And the answer for that is, this is how much uncertainty I have about humidity to start with. And this is how much uncertainty I'm left with on average if I know the temperature. This is very different than the numbers we saw before. This is the very different numbers we saw before. But this number, 0.1345, is exactly the same number we saw before. See, it's the same number. So we have this fundamental observation here, which is not a coincidence, that the number of bits that knowing humidity tells me on average about temperature is the same as the number of bits that knowing temperature tells me on average about humidity. So as long as you keep the words on average in mind, the amount of information that one random variable gives you about another is the same as the amount of information that this other random variable gives you about the first. Causality doesn't matter here. We're not asking about who caused what, if at all. This is about information. Because it is a symmetric quantity, or mutual quantity, it's called mutual information. Let me start with the slide. The technical term is average mutual information, but we call it colloquially mutual information. It is defined as the entropy of a variable minus the entropy of the same variable conditioned on the other variable. H of x minus h of x given y. Or alternatively, h of y minus h of y given x. It is the same. This proves to you that it is the same if you plug in the definitions of entropy and the definition of conditional entropy, and you do a little bit of algebraic manipulation, you can get to this form, which is a really, really nice and interesting form. First of all, it is symmetric. You can see it's symmetric with regard to x and y, so that's the proof that they're indeed the same. But the second thing is you can interpret it as an expectation. An expectation of what? It's an expectation of this part. Right? This is the weighing. So it's an expectation under the joint distribution of x and y. Of what? Of the log of the joint probability divided by the product of the marginal probabilities. It is easy to see from this that if x and y are independent, the mutual information is 0. Because if they're independent, then for any possible value of x and y, little x and little y, the joint is equal the product of the marginals, and therefore the ratio is 1, and therefore log of 1 is 0. And that's true for any combination of values x and y, and therefore this entire sum is 0. So if x and y are independent, mutual information is 0. The opposite direction is less easy to show, but it's also true. The opposite direction is that if x and y are not independent, then mutual information is not 0. In fact, it's guaranteed to be positive. Why is this difficult to show? Because if x and y are not independent, there is a particular set of values x and y such that the joint probability of x and y is different, either greater than or smaller than the product of the marginals. In fact, if there's even one such thing, then there are at least two, because they all have to sum to 1. There are at least two such that for one case of x and y, the joint is bigger than the product of the marginals, and for the other, the joint is smaller than the product of the marginals. When the joint is bigger than the product of the marginals, you get a ratio that's greater than 1, and therefore the log is positive. But for the other case, where the joint is smaller than the product of the marginals, you get a ratio smaller than 1, and therefore the contribution to this summation is negative. Which means that when x and y are not independent, there would be some terms here that are positive and some terms that are negative, and it's not obvious why the sum should be positive. The total combination, the weighted sum. So this part could be positive or negative, and yet the combination is always guaranteed to be positive. So what do we know about average mutual information? First of all, we know it's symmetric. That's why it's called mutual. before I go to second, notice that even though the entropy of x may not be the same as the entropy of y, and the conditional entropy of x conditional on y is not the same necessarily as the conditional entropy of y conditional on x, this minus this is equal this minus this. This is a very nice way of showing it pictorially. If you think of uncertainty as corresponding to area, and you think of a random variable x as having this amount of uncertainty, and a random variable y as having this amount of uncertainty, and this is their overlap, then this is the mutual information between x and y. This part is the conditional entropy of x conditioned on y, and this part is the conditional entropy of y conditioned on x. Notice that the area of y and the area of x are not the same. They could be vastly different, but the overlap between them is of course symmetric. Question?
Does it make sense to think this as the scale diverges from the true distribution to some kind of distribution where we assume that the things are independent even if they're not? It's like the form fit.
The form fit. It's a very nice idea. You're looking at this and you're saying there's a p here and a log of something here, and the something is a ratio which you can break into two parts. And therefore, this is very true. You can think about it, well, I don't want to spend the time on it now because I have 4 minutes, but you're completely right. You can think about it as the KL distance from the joint distribution to something like a product of the marginals. Now is the time to apologize and say I cannot stay for questions today because I'm taking off, leaving town as soon as this lecture is over. So if you have questions, please send them by email or meet with any of the TAs. I apologize. Mutual information is non-negative, and it's 0 if and only if x and y are independent. Something very important about this. Mutual information is defined as h of x, or let's put it this way. One way of saying mutual information is not negative is to say that h of x given y is always less than or equal h of x. In other words, the amount of uncertainty left in x on average after seeing y cannot be greater than the amount of uncertainty that we had in x to start with. So if you're told y, on average, either it affects your uncertainty about x, and or not. If it does, it brings it down. Okay? So knowing another variable, on average, can only help. But I keep saying on average. Why? Because there can be situations where knowing a particular value of y could make your uncertainty about x greater, could be increasing your uncertainty about x. This seems counterintuitive. You have some uncertainty about x. I told you the value of y, and now your uncertainty grows. The answer is yes. Maybe I'll use the remaining minutes to show you this example. Let's see what else I want to show you. Yeah, let me show you this example. Leave you with that thought. All right, you have males and females. You have people who wear glasses and people who don't wear glasses in the class. Let's say males and females are 50 male students and 50 female students. Males, 45 of the 50 students wear glasses and 5 don't wear glasses. And in females, it's the other way around. So Most male students wear glasses, most female students don't wear glasses. Whether you wear glasses or not, clearly is not independent of your gender. How much uncertainty do you have in the random variable glasses, which means 1 for wearing glasses, 0 otherwise? Well, the answer is you look at this distribution here. It's a 50-50 distribution. You have 1 bit, right? Did I give you the right example? No, I didn't give you the right example. 50 minute glasses. Oh, no. Female is 50-50. There you go. 25, and therefore 45 plus 25 is 70, 70 and 30. Okay. Now, how much uncertainty do you have about glasses in general? The answer is it's the entropy of 0.7 and 0.3, which is 0.88 bits. Now you're told that the student is female. And you ask, what is the remaining uncertainty in the glasses situation when the student is female? If the student is female, you know you're restricted to this side, and glasses are distributed evenly among female students, 25-25. And therefore the uncertainty here, 0.5, 0.5, 1 bit. So before you were told the gender of the student, you had 0.88 bits of uncertainty, and now you have more. Of course, the flip side is that if you are told that the student is male, your uncertainty is 0.9, 0.1, which is 0.469. So if you're told it's male, it goes down a lot. Now if you do the average mutual information, namely you average these two, weighted by how likely the student is to be male or female, that is guaranteed to be no more than the original. In fact, it would be less because they are dependent. But it is entirely possible that by being told something, your uncertainty about something else grows. I need to stop here. I think you have enough to do your assignment. If I miss something, please go and check the lectures from previous year. Thank you.